Okay, let's go to Python and convert RGB to HSV, write a code for it that mimic exactly the same algorithm that you're looking in this particular slide. Let's do that. Actually, I already have written this code for you. Let me go through this code line by line and run this code. But let us give a heading here, for example, RGB to HSV conversion. So that's our heading. Now this is the function that I have written for you. F is just for function, and it converts from RGB. It takes RGB and converts to HSV. It actually converts a single pixel just for illustration. So it takes R value from an image for a particular pixel. It takes an R value as an input, G value as an input, blue value as an input, and then it takes a scale factor. For example, if you want this saturation and values to be scaled rather than from 0 to 1, if you want the scale factor, for example, to 0 to 100, and maybe you can have a different scale factor for value, or maybe the same for both. So if you, for example, run the scale, take the scale factor as 1, it is exactly like the slide you are seeing here, but you can change the scale factor for saturation and values to range between 0 to some arbitrary value rather than 1. Because the different implementations in different packages, they have different scale factors. That's why I'm writing a scale factor as an input here. So first of all, you normalize your RGB values by dividing them. Each RGB, you divide them by 255 to ensure that RG and B, all these values are between 0 and 1. Then we compute the max value, just like in slides. We compute the max value here, that value max. We compute the max value of RGB, we compute the min value of RGB, and we compute the difference, which is C max and C min. That difference is required. That difference is required here, max minus min. That is required here. That is required here, here, and here. So let's compute the difference as well. Now, further, if you can notice, because to compute these H values, we are dividing by this difference, which means if max and min, they are equal, then the difference will be 0, and dividing by 0 is not allowed. So we make a separate check for it. If C max and C min are same, which means the difference is, or the divider is 0, then H value is 0. Otherwise, we go to 3 if conditions. If maximum value is R, then we apply this particular if condition, which is 60 times G minus B divided by the difference. So if we just look in here, 60 times G minus B divided by the difference, and then we just over ensure that the value should not exceed 360. This 0 is exactly the 0 we are adding here, so not a big deal. Then if C max is G, then we multiply this thing and this 120. Don't confuse with this 120. If 60 is multiplied by 2, it will generate 120, and then this 60 will be multiplied with this factor, which is exactly here. And similarly, if C max is B, then we got this value. This 240 is again like this 60 times 4 is 240. So after that, we just over ensure that if indeed H value is negative, then we add a 360 to it, this condition. And now we actually go and find out the saturation value. If C max is 0, because the C max is the divider here, max is the divider here. If the divider is 0, we set the saturation to 0. Otherwise, we set the saturation to difference divided by the max value. So that's difference divided by the max value. If C max is 0, then S is 0. Otherwise, you do that. And that's a scale factor that you multiply for S. You can have different scale factors for saturation and different scale factor for value. And the V value is simply the max value as computed exactly here. V is the max value. So that's for 1 pixel. And then you return H, S, and V. Let's run this. Let's run this code. Shift enter, and let's print, for example, print f RGB to HSV, and let's give some values. Let's say the R value is 100, let's say the green value is let's say 200, and let's say the blue value is 50, and the scale factor, let's say the scale factor is 100. We want this saturation from 0 to 100, we want the value from 0 to 100. That's the scale factor. And here you can see the hue value is 100, the saturation value is 75, and the brightness or the value is 78. This is for 1 pixel. If we want to convert an image, complete image from RGB to HSV, we can apply this formula to each pixel, and we can convert, then we will be having H as a matrix, S as a matrix, and V as a matrix corresponding to each pixel. So that's the algorithm for converting RGB to HSV. I can also show you an OpenCV function that actually does that. So for example, let us convert an image. Let's read an image from our image directory and convert that image. For example, im equals cv2.imread. Remember cv2, remember this OpenCV will read the image in BGR format. So that's our image. We have that image. Let's convert that image to HSV. So HSV image is equal to cv2.cvt cvt color, and here we give our image im, and then we set what color we want to convert, cv2 dot color. So color BGR to HSV. So that will convert BGR to HSV because BGR is our original format and HSV is the one we want to convert to. So if we do that, we will get our HSV image, and if we see the type of this HSV image, that again is a NumPy array. If we see the shape of it, HSV image dot shape, we will be seeing the 3 channels rather than RGB. Now we have H, S, and V channels, and we can play all the way. We can, like we were playing with RGB images, we can play with HSV images. And here one thing to notice, that the cvt.color, it has a lot of different conversions. For example, you can convert from HSV back to BGR, you can convert from BGR to RGB, you can convert from BGR to a grayscale, you can convert from BGR to a CYMK. There are a lot of color spaces, a lot of color combinations that OpenCV offers you, and you can play with those. So I hope that you have understood what is a color model, and in particular, how can we convert from one color model to another color model. And in this particular video, I've just given you an example of converting from RGB to HSV. There are different algorithms for converting from one color space to a different color space, for example, a CYMK or maybe another different color space. And in the next video, I will show you that maybe a particular computer vision task may become more easy to perform if we choose an appropriate color space for that particular task. Rather than just working on an RGB image, maybe we can go to another color space and the task becomes just simpler. So in the next video, I will talk about image segmentation using HSV conversion. Hope to see you in the next video.